So, welcome to the course on blockchains, architecture, design and use cases. So, till the last lecture, we have talked about the basic fault tolerant protocols in a distributed system, and we are continuing our discussion from this permission blockchain environment, which mainly follows the principles of a general distributed system. So, we have looked into different aspects of this fault tolerant nature of a distributed consensus protocol. We have looked into the Raft consensus and Paxos consensus protocol in little details, and during that discussion we have understood that the Raft and Paxos, they work good for crash faults, but if there is some kind of Byzantine behavior in the network where the node starts behaving maliciously, then the Paxos and the Raft protocol cannot handle this kind of scenarios. So, on this ground we will look into a different class of fault tolerant protocol for distributed system under the permission or a closed environment, which we call as the Byzantine fault tolerant protocol. So, we will look into this Byzantine fault tolerant protocols in details. So, as we have mentioned that we are talking about this permission blockchain environment, which is a closed environment and every node knows each other, and under this permission model fault can occur, and whenever there is a possibility of having certain kind of faults, during that time you may have broadly three different types of faults. The crash fault, where a node can fail arbitrarily due to crash, that can be a hardware crash or a software crash, and in case of a crash fault it may happen that the node stop transmitting messages to all its peer. Now, the crash faults are kind of recoverable. So, a node can recover from the crash faults after certain duration, and after this recovery from the crash fault, the node can again start behaving normally. But the second class of faults, which is the Byzantine fault, so crash fault has another notion of network fault, where you can have a communication failure between two nodes, and if there is a kind of communication failure between two nodes and it gets repeated, it may happen that the network may get partitioned. Now, if the network get partitioned, during that time you do not have any way to send messages from one partition of node to another partition of node, and you may not be recovered from this correct behavior. Now, if you cannot recover from the correct behavior during that time, you have this kind of consensus protocols like the Raft and Paxos, but if you have the fault like a Byzantine fault, when a network when a node starts behaving maliciously, so in the presence of this kind of Byzantine fault, it may happen that the node sends different messages to different peers. So, here is an example of an Byzantine fault. The fault came from the concept of Byzantine general problem, where the general sends an attack message to one troop, whereas send a retreat message to another troop. Now, if the general becomes faulty, then it becomes difficult for a system to find out what to do. So, we will look into this general class of faults in a distributed system under a closed environment, which we call as a Byzantine general problem or Byzantine fault tolerant problem, and we will try to develop a fault tolerant architecture where the system will be able to tolerate this kind of Byzantine faults. Now, let us look into the Byzantine general problem under multiple node scenario. So, here we are considering the three Byzantine general problem, where you have three generals in terms of these are kind of Lamport's term to denote this kind of Byzantine general problem, and in this architecture you have one commander and two different lieutenants. So, the commander sends the message to the lieutenants, and the lieutenant can share the messages among themselves and try to find out whether the commander is faulty or whether the lieutenant is faulty. Now, let us look into the case from the perspective of three generals. And in this particular case, we will try to design a problem, we will try to design a solution for this Byzantine fault tolerant system. So, in this architecture, we assume that the lieutenant is faulty, Now, if a lieutenant is faulty, then the lieutenant may send different messages from what it hear. So, the commander is a correct commander. So, the commander sends a retreat message to both the lieutenants. Now, this particular lieutenant, this is a faulty lieutenant. So, the faulty lieutenant does not obey the message which is sent by the commander, rather the faulty lieutenant sends an attack message to the other lieutenant. Now, this lieutenant, the second lieutenant, this is a correct lieutenant. So, the correct lieutenant sends the retreat message what he has heard from the commander, the same message is sent to the second lieutenant. Now, under this particular scenario, when the commander is correct, but one of the lieutenant is faulty, let us see that whether we can reach into a consensus under this scenario. Now, in this scenario, lieutenant 1, it receives different messages. So, it receives a retreat message from the commander, and it receives an attack message from the lieutenant 2. Now, in this case, in general principle of a normal army scenario, the lieutenant always obey the commander. Now, with this integrity condition of the army, the lieutenant may obey the commander, and if the commander is non-faulty, then the entire system works correctly. Even if the lieutenant 2 is faulty and the lieutenant 2 sends a wrong message like this attack message to lieutenant 1. So, we see that well, if the lieutenant is faulty, but the commander is correct, then by this general principle of integrity in the army, we will be able to solve this problem, that all the lieutenant will follow the commander. Because the commander is correct, then we do not have any kind of consensus problem in the system. But now, let us look into the second condition, that the commander is faulty. So, this is a kind of non-trivial case, and this is a kind of difficult case which we need to handle in case of a Byzantine general problem with 3 generals. So, in this case, the commander, it sends the retreat message to one lieutenant, and it sends a different message, the attack, to the second lieutenant. Now, in this particular case, we assume that the commander is faulty. So, the commander is faulty, but both the lieutenants are correct. Now, if both the lieutenants are correct and the commander is faulty, and we try to conceive to the integrity principle that we discussed earlier, then this lieutenant 2, it has heard an attack message, attack instruction from the commander, and it sends back or echoes this attack message to the other lieutenant. So, in this particular case, we see that well, by the message passing principle, the entire system will not be able to work, because this lieutenant, it will have so say here this lieutenant 1, it will have different messages from different persons, different generals. So, it will get a retreat message from the commander, whereas it will get an attack message from the lieutenant 2. So, because it has different messages, so it will with the integrity condition, if we try to do a attack, if we try to do a retreat, then it will follow that principle. But whereas this lieutenant 2, it got the attack message, if it attacks, then obviously the entire army will get defeated. So, what we see here, that by this message passing principle, if we try to obey to the commander, and if we do not have any way to find out that whether to go for the majority voting or whether to go for the instruction that the commander has sent, then the entire system is in a dilemma that which particular instruction to follow. So, even under the Byzantine general problem, we can solve this particular problem of Byzantine failure with the principle of majority principle or the majority voting that we have seen in the case of Paxos or in the case of Raft. So, if you remember the Raft consensus protocol, which we have discussed in the context of a crash failure, that the entire system works on the principles of a leader. So, in case of the Raft consensus, we had the concept of the leader, and what the leader says, all the other followers will follow what the leader instructs. But in this particular case, when the system is a kind of Byzantine system, and the leader itself. So, here the commander, if it sends different messages to different lieutenants, then coming up to a consensus on this principle becomes difficult. So, under this particular scenario, what may happen, so the protocol abstraction that we are looking into with the help of an example, that the lieutenants or the followers in the rough consensus terminology, so the lieutenants can start sharing the message among themselves, and they can look into this majority principle construct like, well, if the majority persons or the majority of the lieutenants votes against the commander, then we will assume that the commander is faulty. Otherwise, we will consider that the lieutenant is faulty if we are not getting majority voting, rather some individual lieutenant who are differing from the message which is sent by the commander. So, if we try to apply this majority voting principle, what we see that with 3 Byzantine generals, with 1 commander and 2 lieutenants, the problem still remains unsolvable, because the majority principle does not work. You get equal voting for attack and retreat, or a lieutenant gets equal voting for attack and retreat, and the lieutenant cannot decide what to do. And if the lieutenant at that time tries to follow what the commander has asked him to do, then the lieutenant can take a decision which differs from the decision taken by the other lieutenant. So, we will not be able to solve the Byzantine general problem with 3 generals, where we have 1 commander and 2 different lieutenants. So, that is one learning, that well, we will not be able to solve the Byzantine general problem with 3 different 3 different generals with 1 commander and 2 lieutenants. But let us look into another use case if we have 4 different Byzantine generals. So, with these 4 different Byzantine general, we have 3 lieutenants, and every individual lieutenant, with the message passing principle that we have discussed earlier, they talk with each other. So, here in this case as well, the commander it sends the message to all the lieutenants, and the lieutenants, they share the message what the commander has shared with them with each other. But as we have discussed earlier, that the lieutenant can be faulty, and in this case we assume that 1 lieutenant is faulty. So, we have 1 faulty lieutenants, 1 faulty lieutenant. Now, among these 3 lieutenants, if 1 is faulty, let us see what happens for the 2 different cases. So, the first case we are going to consider is the lieutenant is faulty, and the second case we will look into when the commander is faulty. Now, when the lieutenant is faulty, so the lieutenant sends messages which differ from the messages which is sent by the commander. Now, the commander here sends the retreat message to all the lieutenants, and this lieutenant 1 and lieutenant 3, they correctly echoes the message to other lieutenants. So, this lieutenant 1, it informs retreat to lieutenant 2 and retreat to lieutenant 3, but lieutenant 2 differs. So, because lieutenant 2 is a faulty node here, the faulty general here. So, the lieutenant 2 incorrectly echoes the message to others. So, the lieutenant 2 sends an attack to lieutenant 1, and similarly it sends an attack to lieutenant 3, whereas the commander has sent to retreat from the where. Now, let us see what happens. So, here in this case, if we go for the majority voting principle. So, we are going with the majority voting principle. So, with the majority voting principle, we see that for these lieutenants, it receives 2 retreat message, 1 retreat message from the commander, second retreat message from lieutenant 3. So, the majority is lieutenant. So, this lieutenant 1 is able to correctly decode what the commander has actually instructed for. Now, in the second case, let us see what happens for lieutenant 3, which is a correct lieutenant. So, the lieutenant 3 receives a retreat message. It receives this retreat message from the commander. It receives another retreat message from lieutenant 1, but it receives an attack message from lieutenant 2. Now, again if we go for the majority voting principle, with the majority voting principle, it receives 2 retreat messages and 1 attack messages. So, with the majority voting principle, it decides to retreat from the where. but this lieutenant is faulty, we do not consider the behavior of the faulty lieutenants. So, in this case we observe that well our objective of a fault tolerant algorithm, if you remember, was the integrity principle, like that all the correct lieutenants or all the correct nodes in a fault tolerant system, they will follow the majority votes. So, here we observe that even if lieutenant 2 is a Byzantine node, then also lieutenant 1 and lieutenant 3 is able to correctly decode the message from the majority voting. Now, if we further consider the majority malicious behavior or the Byzantine behavior of lieutenant 2. So, instead of sending an attack, if the lieutenant 2 sends an retreat here, so it is like that the lieutenant 2 is making a malicious behavior where it is sending the correct message to one node. So, it is sending attack to one node and it is sending this false message to one node and the correct message to another node. Even in this case, you can find out that well this particular lieutenant, it gets all the retreat message, so it remain retreat, whereas this with the majority voting principle, lieutenant 1 can correctly decode the message. So, with the lieutenant faulty, or better to say with one lieutenant faulty, we can correctly decode the message in case of this Byzantine general problem. But instead of one lieutenant to be faulty, if we take a different case where two lieutenants are faulty, say here we assume that this particular lieutenant is faulty and at the same time lieutenant 1 is also faulty. If it happens, then lieutenant 1 can also start behaving maliciously, and rather than the correct retreat message, if it sends the attack message at this stage, so if it sends an attack message at this stage, then we see that well for lieutenant 3, lieutenant 3 receives one retreat message from the commander, but two attack message, one attack message from the faulty lieutenant 2 and another attack message from the faulty lieutenant 1. So, it will not be able to take the correct decision based on the majority voting. So, here we observe that well out of the 3 lieutenants, if one lieutenant is faulty, then we will be able to correctly decode the message. Well, now let us see the second case of this problem with 4 Byzantine generals when the commander is faulty. So, the commander is faulty means the commander is starting behaving maliciously. Now, in this case, in this malicious behavior of the commander, now say the commander sends the retreat message to one lieutenant, the retreat message to the second lieutenant, but an attack message to this lieutenant 2, the third lieutenant. So, if the commander starts behaving maliciously, but the lieutenants are behaving correctly, let us see what happens. So, in this case the lieutenants, all the lieutenants are correct, because all the lieutenant is correct. This lieutenant 1, it has heard a retreat message from the commander. So, it correctly echoes the retreat message to other 2 lieutenants. Now, lieutenant 2, it is again a correct lieutenant, but it has heard an attack message. So, this lieutenant 2 sends an attack message to the other 2 nodes, whereas lieutenant 3, it is a correct lieutenant as we have seen earlier. So, the lieutenant 3 has heard an retreat message. So, it correctly broadcast the retreat message or let us say multicast the retreat message to other 2 lieutenants. Now, let us see whether the majority voting works in this case or not. So, we first look into the case of lieutenant 1. So, lieutenant 1 has received 1 retreat vote, then 2 retreat votes and 1 attack vote. So, it has received 2 retreat votes and 1 attack vote. Because it has received 2 retreat votes and 1 attack votes, it can currently decide that the decision is retreat. Now, for lieutenant 2, it has received 1 attack vote from the commander, but it has received 1 retreat vote from lieutenant 1 and another retreat vote from lieutenant 3. So, it has lieutenant 2, it has received one attack vote from the commander, one retreat vote from the lieutenant 1, another retreat vote from the lieutenant 3. So, it can decide based on the majority principle that the retreat is the correct decision, and if retreat is the correct decision, it can correctly finds out that the commander was indeed faulty. Now, let us look into the case for the third lieutenant. For the third lieutenant, we have for the third lieutenant we have this retreat message which has been received from the commander, then one retreat message which has not this one, this retreat message which has been received from lieutenant 1, and one attack message which has been received from lieutenant 2. So, it has received retreat message from commander, retreat message from lieutenant 1, but attack message from lieutenant 2. So, again from the majority voting principle, it can decide that the correct decision is retreat. So, again in this case we can observe that if you have 3 different generals who are correct, or better to say 3 different lieutenants who are correct, and you have one commander who is behaving maliciously, again you need to ensure that you can ensure that the majority voting principle will give you the correct results. Now, if we look into a general principle, in that general principle, if we look into the normal Byzantine general problem with f number of faulty nodes, then we can say that if a lieutenant is faulty, in that case we need to ensure that there are 2f plus 1 number of correct 2f plus 1 number of lieutenants, total lieutenants in the system. So, if we have 2f plus 1 lieutenants plus 1 commander, then we will be able to correctly apply this majority voting principle to find out the Byzantine nodes in the system. Now, again in this entire system, if we see that if the commander sends message or this attack message to more than one lieutenant. So, if it sends attack message to this lieutenant and rather than a retreat, if it sends to a attack message to this lieutenant as well, then whatever majority decision or the majority message that the commander is sending, the entire system will come to that, or will take that particular message in the consensus. So, if the commander is sending 2 attack message to 2 lieutenants and 1 retreat message, then in the consensus the entire system will reach to the attack message by this majority voting principle. So, our learning or our takeaway from this discussion is that if you have this 2f plus 1 number of lieutenants and 1 commander, and out of them if the lieutenant is faulty, then the system will come to a consensus with the value that the commander has proposed, and if the commander is faulty, in that case the system will come to a consensus with the value that the commander has proposed to majority of the lieutenants. So, that way we can come to the consensus with 4 Byzantine generals, and let us try to look into a general description of this particular algorithm. So, the algorithm works in this way. We call this entire model as Byzantine general model. So, in this Byzantine general model, we assume that there are n number of process, out of which at most f number of process can be faulty. Now, when we say f number of process are faulty, we need to ensure that in the system we have 2f plus 1 number of lieutenants, 2f plus 1 number of lieutenants in the system, and the receiver, it always knows the identity of the sender. So, that is our closed model. In the context of blockchain technology, this model help us to design an algorithm for the permission blockchain environment. So, the system is fully connected. the communication is a reliable communication medium and the system is synchronous. So, system is synchronous means every node will be able to receive all the messages within some predefined timeout duration. So, remember the impossibility theorem in this context that we discussed earlier, that in a fully asynchronous system, even if a single node is faulty, the system will not be able to reach to a consensus within a predefined timeout interval. So, we do not look into the asynchronous nature of the system at this moment. So, we are trying to develop an algorithm which is synchronous in nature. So, this synchronous algorithm, this particular algorithm that I have just discussed right now with an example. So, this algorithm is known as Lamport-Shostak-Pease algorithm, which was one of the first algorithms for having this kind of Byzantine general problem that was published in this ACM transaction on programming language and system. The title of the paper was the Byzantine general problem. So, in this particular case, the commander sends the message at pulse 1. So, the pulse 1 is the initial pulse when the commander sends the message to all the lieutenants. So, we are first considering a base condition. So, this base condition we have two parameters here, n is the number of processes that are there in the system and t is the algorithm parameter that denotes the individual rounds. So, t basically indicates, t equal to 0 indicates that you are in pulse 0 when the commander is sending a message to all the lieutenants. So, the commander it decides on its own value whether to go for a retreat or to go for an attack, and at pulse 0 it broadcasts this particular message. So, here it is the retreat message as an example to all the lieutenants. So, here we consider n equal to 3 because we have 3 different processes among which we are trying to reach to the consensus. So, we send 3 messages to 3 different lieutenants. Now, that is the base condition for the commander. Now, let us look into the base condition for a lieutenant. So, the lieutenant it receives the message from the commander. Whenever it is receives the messaging from the commander, it first task is to check whether it is a pulse 1 message or not. So, it is a pulse 1 message means that the message is coming from the commander. If it is no, that means it is not a pulse 1 message, then you cannot take any decision because you do not know that from where the message is coming from. If it is a pulse 1 message, that means the first message in the system and the message is coming from the commander, then you accept what the commander is saying. Otherwise, the system goes to the undefined state. So, what the commander is saying, you then broadcast that particular message to all other processes in the system. So, that is the initiation. Now, at every individual round, the system progress in route as we have mentioned. So, at every individual round, commander T, so we can say that this is a commander, the commander end commander. Sorry, you can just think of it as Tth commander or commander T, who is sending this message. So, this commander T it broadcast again the message that it has received from the commander. So, this is the commander. So, the commander it sends this message to all the lieutenants in the Tth round, and similarly for the lieutenants, every individual lieutenants, whatever message it receives from the commander, it broadcasts this message to all other lieutenants except the sender of that particular message. So, it does not broadcast a message to the commander, rather it broadcasts this message to all other lieutenants in the system. Now, with this broadcasting of messages at every individual round, what may happen if you have n number of lieutenants in the system, then after nth round you are getting the messages from all the individual lieutenants, and as we say that the system is synchronous. So, you are known to get the messages from all other lieutenants who are there in the system after the nth round. So once you receive all these messages, then you can apply the majority voting principle. So every individual lieutenant, they apply the majority voting principle, and by applying the majority voting principle, they decide based on the majority voting what should be their decision, whether the decision would be to go for what the commander is saying or to go for what the commander is saying to the majority of the lieutenants. So the example that we have seen for the 4 general problem. So here in a general condition, the algorithm, as I have mentioned, that the algorithm works in this principle, like the commander at every individual round, the commander is sending the messages, broadcasting the messages to every individual lieutenants, and once this lieutenant get the message, it again broadcast that message to other lieutenants except the sender. So here the sender is the commander. So every lieutenant gets the messages from all other lieutenants along with the commander, and they apply the majority voting principle. What the majority voting says, it takes that particular decision. So this is a algorithm for achieving consensus, which was developed primarily by Lamport for a synchronous environment, when you know that you are going to receive the messages within some predefined timeout interval, and if you are able to receive the messages within a predefined timeout interval, then you can apply the majority voting principle to decide what should be your decision. So if the majority voting principle says that you go for attack, then you should go for attack. If the majority voting says that you should go for retreat, then you can go for retreat. And in this case, if a lieutenant is faulty, until you have sufficient number of lieutenant in the system, like if there are f number of lieutenants which you are assuming to be faulty, and you have 2f plus 1 number of lieutenant in the system, you can safely assume that with the majority voting principle, you will accept only the message which the majority of the correct lieutenant says. Now, if the commander is faulty, in that case the scenario is little tricky, that the commander is sending one vote to one group of lieutenants and another vote to another group of lieutenants, and if you have 2f plus 1 number of lieutenant in the system, so you can just think of in this way, that if you have 2f plus 1 number of lieutenant in the system, you always have some odd number of lieutenants, and when the odd number of lieutenants, the commander has no way of saying some majority decision. Say for f number of lieutenants, it will say one decision, and for remaining f lieutenants, it may say another decision. So what the commander is saying, in this case, what the commander is saying to the majority of the nodes, you will be able to decide on that majority voting, on that majority value. So in this case, with 2f plus 1 number of lieutenants and one commander, we can achieve consensus in a synchronous system when you have either the commander is faulty or one of these 2f plus 1 lieutenants are faulty. Sorry, not one of 2f plus 1 lieutenants are faulty, the f number of lieutenants are faulty. So if f number of lieutenants are faulty, with 2f plus 1 number of lieutenants, you will be able to achieve consensus. Otherwise, if the commander is faulty, but all the lieutenants are correct, then also you will be able to achieve consensus under this Lamport's algorithm. So this is an consensus algorithm which is for a synchronous environment, but as we understand that our practical networking systems environments are asynchronous, which does not behave like a synchronous environment, and in that asynchronous network, it may happen that you will not be able to receive message within a predefined timeout. So in the next class, we will look into another class of consensus problem, which can work, or which we say that it provides safety principle or safety guarantee for asynchronous network, but there is certain condition on the liveness principle. We call this algorithm as the practical Byzantine fault tolerant algorithm, or PBFT algorithm, which is widely used in a blockchain environment. So in the next class, we will look into the PBFT algorithm in details. So thank you for today's class.